In today's lesson, we're going to be talking about vector and parametric equations of a line. So to talk about vector equations of a line, that's what we're going to start with first here. We're going to start ourselves off with a point and a vector. This vector is vector D, it's labeled that here. So what we want to do is find the vector equation of a line is you want to find all vectors that start at the origin and go to a point on this line. This line is dictated by two characteristics, the point and what's called its direction vector. You can think of the direction vector as the slope of a linear equation. So if you recall, with linear equations, we needed a slope and a point. With vector equations, we require a point and a direction vector. Now, as we know, we can't add a point and a direction vector together, so what we're going to do here is we're going to create the vector OA, and we'll label that as R0. So now we have a second vector here, going from the origin to point A, and I will label that as R0. So now, like we were talking about, we want to create a vector equation of a line. So I'm going to take my direction vector here, and again, you can think of your direction vector as your slope. As I move this direction vector to the tip of vector R0, we now can sum these two vectors. Summing these two vectors, we have R0 plus D, and notice now we have a vector that goes from the origin to a point on this line. Now let's say we took that D value, and let's say we, instead of adding D, we added 2D. Well, if we go ahead and do that, we now have R0 plus 2D, and the resultant vector would now go to here, and this would be vector R0 plus 2D. Likewise, I can go ahead and add negative D, and now the direction vector is going to go in the opposite direction, and the resultant vector would now go to here, and therefore this vector would be R0 minus vector D. Continuing on in this way, we could also subtract 2D, and now the resultant vector would be R0 minus 2D. And continuing on in this way, we can go ahead and you can add half D, in which case maybe it would go to here. And by doing that, you have another resultant vector right here, and that would be R0 plus 1/2 D. And I think you guys are starting to get the idea. You can also do R0 minus 1/2 D. And you can see here that every resultant vector that we have ends up finishing at a point on the line here. So in general, what we're doing is the vector equation of this line, which we denote with a V, is going to equal what? Well, it's going to equal the collection of all R0 plus some scalar multiple times my direction vector. And that scalar multiple is any real number. If I let t be 0, we're grabbing our initial point that we started off with. If I let t be 1, we're going to be starting at the origin and going to this point here. If I let t be 2, we're going to start at the origin and go to this point here. If I let t be -1, we're going to go here, etc., etc. And what you end up collecting up is the collection of all vectors that start at the origin and go to a point on this line. So in general, the vector equation of a line can be expressed as R0 plus t times its direction vector, where R0 is a vector that starts at the origin and goes to some point, and D is the direction vector of the line. Notice that your direction vector acts as a slope in relation to linear equations. So for the following example, this vector equation, V, would be equal to the vector 1, 4 plus t times any scalar multiple of our direction vector -3 and 2. This would be considered the vector equation of the line. Parametric equation of a line is fairly easy to solve for. For parametric equation of a line, the first coordinates here represent my x coordinates. So your parametric equation will be x equals to 1 minus 3t. Again, I'm just adding these two. These are two vectors. You can add vectors coordinate-wise, so the x coordinate of this vector would be represented as 1 minus 3t, and likewise the y coordinate of this vector would be represented as 4 plus 2t. So here we have an example of vector equation of a line and the parametric equation of a line. Let's look at some more examples. For our first example here, we want to find the vector and parametric equation of a line given 2 points. So now we have these 2 points here, E and F, and we want to find the vector equation of this line. So I want to be able to find all vectors that go from the origin and are going to hit all the points on the line that goes between E and F. Well, how do we find the line that goes between E and F? What we're going to do here is we're going to calculate vector EF. This will give us our direction vector. So calculating vector EF, we end up getting 7 and 6. So vector EF is the direction vector 7, 6. Now therefore, if we want to calculate the vector equation of a line, we only need a point. We can choose either point. I can choose point E or point F. Does not make a difference. So in this case here, so choosing the vector OE, for instance, we could have vector -1 and 5 plus any multiple of our direction vector 7, 6, and t is any real number. Equivalently here, I could define vector v to be the vector 6, 11 plus any scalar multiple of 7, 6. Notice here I chose a different scalar multiple. This time I chose the scalar parameter of s. The reason for that is I don't want you to think that they are the same at the same time. Right? But these will both generate the exact same equation. The reason for that is, let's say we chose the vector -1, 5. -1, 5 is going to be this vector here plus your direction vector 7, 6, which will kind of go along that line, and you'll be able to get all the points along that line. Or if I would have chosen this vector first, we have the same direction vector, so it can go in the same direction, adding these resultant vectors here, and again that'll get all the points along this line as well. So for instance, notice that the direction vector is not unique. You can do any scalar multiple of this direction vector and it'll still generate the equation of the line. I could define my direction vector, for instance, to be 7/5 and 6/5, and in which case one possible vector equation that would be equivalent to the above two would be the vector equation 6, 11 times any multiple of 7/5 and 6/5. Also notice the parametric equation of this line would be x equals, referencing this equation for instance, would be x equals -1 plus 7t and y equals 5 plus 6t, where t is any real number. Another common question that's asked regarding this problem is a certain point on the line? So is a certain vector part of the vector equation? Well, if vector -2 and 3 is on the line, then it must be the case that for some variable t, again, I'm just going to reference our first vector equation we created. You can do the same with any of them, but just referencing our first vector equation, there must be some value of t such that -2 and 3, vector -2 and 3 is equal to vector -1, 5 plus that scalar multiple, which must mean that in parametric form, -2 must equal -1 plus 7t, and 3 must equal 5 plus 6t. Well, solving for t for our first equation, we get -2 equals -1 plus 7t, 7t equals -1, t equals -1 over 7. However, solving our second equation, we have 5 plus 6t equals 3, 6t is -2, and t equals -1/3. So therefore, we require different t values so that each coordinate would be equal. So the conclusion here is that the vector -2 and 3 is not part of the vector equation of this line. Had they come out to be the same, then it would have been a part of the line. Let's look at another example using this same problem. So referencing the problem above, we have found the following vector equation. Now what we want to do is find the vector equation that's perpendicular. Keeping in mind the connection between linear equations and vector equations of lines, notice that we want to find a vector that's perpendicular to my direction vector. Again, any point on this line here consists of, in this case here, this is our vector -1, 5 plus our direction vector, some multiple of our direction vector. So along this line here, we have a lot of different direction vectors of different lengths in different directions. So what we want to do is find a direction vector that's perpendicular. So therefore, we need to find a vector that meets this line at 90 degrees. So therefore, we have to find a vector whose dot product with 7, 6 is 0. Therefore, expressed in dot product form, we have our vector 7, 6 dot product with the unknown vector AB that we want to find must equal 0. Expanding this out, we have 7a plus 6b equals 0. Notice here we have infinite solution. We have one equation, two variables. Now we need a solution that's non-zero. A and B can't both be 0 here. So in this situation here, notice one possible solution is to let A be 6 and B be -7. Substituting that into the equation, notice it satisfies the equation. So therefore, one possible vector that we could have chosen for a direction vector that's perpendicular to 7, 6 would be the direction vector 6, -7. Notice in general, given a vector AB, if you want to find a vector perpendicular to that, just take its dot product with B, -A. Expanding this out here, we get AB minus BA, which is 0. So therefore, one possible answer for a vector that's perpendicular to our vector equation that we found above would be the vector equation -1 and 5 plus any scalar multiple of 6, -7. Notice here that what we're finding is a vector equation that's perpendicular to this line here, but our vector equation that we've chosen here goes through the point -1 and 5. Similarly, just like linear equations, we could have chosen another value. I could have, for instance, chosen the point 611 plus a scalar multiple of 6, -7, and that would also represent a vector equation that is perpendicular to the following vector equation that we have here. All right, that concludes today's lesson. Thank you.